So, I'm not at my best right now. And I thought that maybe, instead of coming in tomorrow and trying to teach a class like this, I could just do it now. Here, where I can wear comfy Malamute slippers and pass out if I need to. Or cut the video before I go into a coughing fit. So, first things first, you don't get out of the hard questions just because this isn't real. So take a minute and think about what we did last time. Write it down. Don't use your notes. I'm gonna go get some orange juice while you work on that. Bad news, no orange juice. Good news, plenty of Ben & Jerry's. Moose pie, that's a new one. We're gonna try it. So what did we do last time? Well, we've been talking about probability. And we started off with just this basic definition of what it means, right? It colloquially means successes over total. What percent of everything that could happen is this event, right? When we look at rolling a die with a six-sided die, right, and asking what's the probability that I get a 6? Well, out of the 6 possible outcomes, one of them is a 6, which means I got a 1 in 6 chance, right? 1/6 of the time I should be rolling a 6, assuming it's a fair die. And that's what we wanted to do with everything, but we hit a snag because that requires us to be really good at counting, and sometimes counting is surprisingly difficult. So we spent a section on combinatorics, learning how to count really well. And now we've gotten into this third section where we're kind of leaning more into that original definition of probability, the probability of a single event. And we've been using combinatorics to help us count how many of all the possible outcomes are in our event. Also, how many possible outcomes are there? Now, we've talked about 2 things with that so far. First, we talked about how combinatorics helps us count those events. It helps us count how many total outcomes are possible in the experiment. And then it helps us count how many outcomes are possible in our event so that we can look at the ratio of those 2. And then the last thing we talked about was number 2, that sometimes the opposite is easier. We know that either an event happens or it doesn't, right? And so the sum of those 2 probabilities, it has to add up to 100%. So if I'm having difficulty finding the probability of an event E, I can find the probability of its opposite, the complement, E complement, and then I can just subtract that from 100. There's only one more thing in this section that I want to touch on here, and that's this, number 3. There's a difference between probability and odds. We actually talked about this before. I thought that the book skipped it, but apparently it does it here instead. And so we talked about this when we looked at roulette, and we talked about the difference between probability and odds, and how odds relate to the fairness of a game. But I guess we'll get back into it here. We might as well. So here is the official definition. For an event E, the odds for E is the ratio of the number of outcomes in E to the number of outcomes in E complement. The odds against E is the opposite ratio, the number of outcomes in E complement to the number of outcomes in E. Let me take you back to roulette for a moment. When we looked at roulette before, we said that there are 38 total possible outcomes. These 38 possible outcomes. You got the 36 main numbers on the wheel, the 1 through 36 that are red and black, and you got the two goofball numbers of 0 and 00 that are green. And we said if you wanted to work out the probability of winning, like if you bet on black, for example, we'd be saying, well, I got these 38 total possible outcomes. What fraction of them are in my event? Out of these 38, how many, what percent of them are in the event that I'm interested in that are black? And in this case, 18 of them are. Out of the 38 total possibilities, 18 of them are in this event. And so we said the probability here is going to be 18 out of 38. That is the fraction of the total amount of outcomes that would be in my event. And if I were to play roulette and bet on black over and over and over again, I would expect to win that percent of the time if I were to divide that and get that as a decimal. But odds looks a little bit different. Odds doesn't compare our 18 outcomes that are in the event to the total amount of outcomes. Instead, it compares them to all of the outcomes that are not in the event. And wow, that's really bright. Actually, that kind of hurts my eyes. And so the odds for this event would still be using that 18. I've got 18 outcomes that are in my event, but now I'm comparing it to the 20 outcomes that are not in my event, not the 38 total, but the 20 that aren't. And I'd be comparing those two. Those are the odds for my event E. And if I were to just flip it around, I would get the odds against it, 20 to 18. Right? Instead of looking at the 18 outcomes that are in the event compared to the 38 total, I've got the 18 outcomes that are in my event E compared to the 20 outcomes that are not in my event E, that are in the complement of E, the opposite of E, not E. I'm comparing those two. And I'm using the colon here to show that this is more of a traditional comparison. It's a ratio. It's still technically a fraction, but it's focused more on comparison. I'm comparing the number of outcomes in the event to the number of outcomes not in it. But I could still write it as a fraction. I could divide these. And often we're kind of interested in that because that's telling us how much bigger one thing is than another. If I were to divide the odds against E, if I were to pull out my calculator and do 20 divided by 18, which if I do I get 1.111111, that tells me that I'm 1.111111 times as likely to fail as I am to succeed. It tells me how much bigger one set is than the other. Let's look at another example. At Devereaux's Palace Casino and Resort, we have a game on the main floor that we like to call Pull Balls Out of a Bucket. Classic. There's a bucket with 20 balls in it, and 14 of them are golden balls. The others are death balls that have a skull and crossbones on them. If you pull out 2 golden balls, then you win. Otherwise, you lose. The game pays what we call even money, and by that I mean a payout of 1 to 1. You bet $1, you win $1. Now naturally our question's going to be, well, how likely are you to succeed in this? It kind of seems like it would be a shoo-in for you. Shoot, almost 3/4 of the balls are golden balls. You just got to pull out 2 of them. Feels like this should be a landslide victory for us. Let's have a look. Okay, so 20 balls, 14 gold, and 6 crossbones. You win if you draw 2 gold out. What's the probability that you win? I encourage you to pause the video here and take a moment to see if you can work this out, because you have all of the tools to be able to work this out. What is the probability that we win? Well, what are we doing? What is the experiment? Am I doing things in stages? Not really. Am I putting things in order? Definitely not. Am I making a selection from a group of things? Yeah, I'm definitely doing that. What's my group of things? It's the 20 balls in the bucket. And how many am I selecting? I'm selecting 2 of them. So as in the experiment at large, right, my total number of possible outcomes here is going to be 20 choose 2. What about in my event? What am I doing in the event? Again, I am making a selection from a collection of things. What is my collection of things? It's golden balls in the event. That's what I have to select from. There's 14 of them, and I am again selecting 2, so I would have 14 choose 2 ways to select 2 golden balls. If I work these out on my calculator, 14 choose 2 is 91, 20 choose 2 is 190, so the probability is 91 over 190, which is only a 47.89% chance. That's maybe kind of surprising. Maybe it seemed like we would have, a better than 50% chance of winning at this, and honestly, this is one of the things that casinos like to prey on, is as people, we're not always great at determining the likelihood of something. It actually can be a real big problem sometimes. One of my hobbies is video game development, and that's something that I have to think about a lot, is especially in video games where random chance is a big thing and probability is a big thing. From what I've read and learned, a lot of video game developers think about randomness from the light of their players who aren't good at thinking about randomness, and you see this in games where maybe you've got like a 33% chance of landing an attack, and your average player who doesn't think about math that much might think that means if they miss their first 2 shots, they're guaranteed to make the third. That's not true. That's not how randomness works, right? If you were to roll a die and you're looking at, do I get a 5 or a 6? Well, just because you didn't get a 5 or a 6, the first 2 rolls doesn't mean you're guaranteed to get on the third roll. That's not how random chance works out in real life. But game designers have started affecting that. They've changed that aspect of their games to make it more aligning with what the player is expecting and prefers their experience to be. You also see them kind of upping the numbers in a lot of ways, where players think they have a good grasp of how good a chance 90% is, but you really don't. 90% is not as good a chance as you think it is. And so sometimes the game will say that you've got a 90% chance of something working, but then back in the code, there's actually only like there's actually like a 99% chance, because that's what people think 90% means. Anyway, that's the probability that we're successful at this game. What are the odds against you? Well, let's start with the odds for you. We've actually done a lot of the heavy lifting already, because we've seen out of the 190 possible outcomes, 91 of them result in success for you. But then how many would result in failure for you? Well, if there's 190 total outcomes and 91 of them are good, that means the remaining 99 would have to be bad, right? If there's 190 total, if 91 of them are in the event, then the other 99 are not in the event. They're in E complement. So the odds for you would be 91 to 99. Simple as that, then the odds against you would be 99 to 91 would be the odds against you. So those are the odds against you. That doesn't simplify in any nice way. Keep in mind this is like a fraction, but that doesn't clean up in any way. That brings us to our last question. Is the game fair? You might remember me talking last time we talked about odds, about how in a fair game the payout matches the odds against you. In this case, we know the odds against you, 99 to 91. If you think of that as a fraction, 99 divided by 91, that's about 1.09. That's what the odds against you work out to be. What does that 1.09 mean? It means that if you play a lot, you will lose 1.09 times as much as you win. The collection of losses is 1.09 times larger than the collection of wins. Now that's important, because the payout is 1 to 1. 1 divided by 1, which is 1. The odds against you are bigger than that, meaning they're worse than that. The payout acts like you're gonna win as much as you lose, that it's balanced, right? That they're the same size, but that's not the case. The payout acts like you're going to be getting the same amount of wins as you are losses, but in reality, you're going to be losing 1.09 times as much as you win. So no, that's not a fair game. The odds against you are higher than the payout. Now, if the odds against you had been lower than the payout, well, that also wouldn't be a fair game, but at least that would be in your favor instead of the casino's. Let's take a look at this one. Suppose the probability of winning a game is 13 over 35. What are the odds for you? What are the odds against you? I want to do a quick example here about just converting between the two. This has a pen, right? Does that work? Oh, I'm sure this is going to be a great idea. The probability is 13 over 35. What are the odds for you? Well, I've already been told that there are 13 winning outcomes for me, right? There's 13 outcomes that are in the event of me winning. So how many are losing? Well, there's 35 total, and there's 13 that are in my event. So if I want to know how many are losing, I would just have to do 35 minus 13, which is 22. So the odds for me are 13 to 22, meaning the odds against me are 22 to 13. Crushing it. Alright, suppose for a different game that the odds against you are 7 to 3. What's the probability of winning? Okay, well now I want to go the other way. The odds against me are 7 to 3. That means the odds for me are 3 to 7. Make this nice and thick. 3 to 7. So if these are the odds for me, then what is the probability that I win? Well, I know that there's 3 winning outcomes for me, but how many total outcomes are there? Well, there's 3 winning ones and 7 losing ones, so I guess there must be 10, right? The probability of my success must be 3 out of 10, which is a smooth 30%. I gotta be honest, my handwriting actually ended up being a lot better doing this with a mouse than it is on the whiteboard in real life, so maybe we should do this more often. Yeah, I've got to try with a buddy here. If you have a buddy near you, then definitely use them. But otherwise, take a moment and think about this on your own. I've got a great, thrilling game where you flip a coin and roll a single die. If you flip heads and roll an even number, you win. Otherwise, you lose. I'm offering a payout of 3 to 1. I want you to pause the video here and work out these 3 questions. What are the odds for you? What are the odds against you? And is this a fair game? Pause the video right now and give it a whirl before I come back and walk you through it. Well, I hope you took a minute to try to work it out. I took a minute to eat some ice cream. It's so soft now, guys. It's so soft. It's like my dog's ears. So, okay, this is a very thrilling game, it seems. You flip a coin and roll a single die. If you flip heads and roll an even number, you win. Okay, well, we can think through then, what are all of the total outcomes that are possible? I'm flipping a coin and rolling a die. What is the experiment? Okay, what am I doing? Is it something that's happening in stages? Yeah, that's exactly what's happening, right? I have stage 1 where I flip a coin, and I've got stage 2 where I roll a die. There are 2 outcomes for flipping the coin and multiplication. There are 6 outcomes for rolling the die for a whopping total of 12. Cool. Alright, in how many do I win? Well, okay, I'd have to flip heads and roll an even number. There's only one way for me to flip heads, and I have to roll an even number. There are 3 ways for me to roll an even number. I could roll 2, 4, or 6. So, the total number of outcomes in which I'm a winner is 3 over 12. That's 1/4, or 25%. What are the odds for me then? Well, I could work off of this 3 over 12, or I could work with the 1 over 4. They're both valid. Remember that odds are also a fraction. They are a ratio. They can be reduced just like probability can. So I'm gonna stick with my 1/4 here, because I feel like it's the easier one to work with. What are the odds for me? Well, I've only got one winner out of all of these. And I've got, okay, well, how many losers then? Well, there's, kind of 4 total here. That would leave me with 3 losers. By the way, if I were to have gone off of my original, 3 out of 12, it would have been essentially the same kind of thing. I would say I've got 3 winners, and then I've got 9 losers, but this can reduce in the same way because I'm just interested in size, right? If I call it, 3 over 9, or whether I call it 1 over 3, it's all the same. It's all the same to me. I'm just interested in that comparison, not in the exact numbers. So the odds for me are 1 to 3, meaning the odds against me are 3 to 1. Is this a fair game? Well, surprisingly, yes, actually, because a game offers a payout of 3 to 1. And 3 to 1 is the odds against me. Those do actually match. So, yes, this is a fair game. Fancy that. That's all I've got for this section, and honestly, that's all I'm interested in doing with this. I've covered a little ground, and that's good enough for me. If you have any questions on any of these, please feel free to reach out to me. I'll respond to email as best I can, or we can meet virtually if you so desire. In the meantime, get some sleep, get some rest, stay healthy.